Okay, guys, we have here uh, a not new but rather a less popular topic which discusses also some issues in ductility. This was actually uh, an alternate provision in the ACI code way back in the 90s, but I think this is already a part of the code now on the consideration for uh, the failure mode, no? Considering the failure mode of beams and also columns, no? In general, because this can be applied to both beams and columns, or what you call the actual flexural members. Okay, so we have the compression controlled and the tension controlled sections. When you say control, we simply refer to how your member will behave in terms of ductility. Okay, so will it be uh, ductile in terms of the amount of steel reinforcement and of course the geometry of the section, or will it be brittle in the sense that the type of failure uh, is initiated by crushing of concrete and yielding of steel. In my readings in the topic of ductility, and in some researches, in most researches that I have read, I always uh, have encountered that the failure of members in especially flexural members are always initiated by crushing of concrete. And in that kind of failure, we have to take note that if there is no ductility in it, the failure mode is sudden, and you call that a brittle failure, and that is a very dangerous type of failure, no? That we don't want to happen in our structure. So to go into the detail of this topic, if we consider now a beam here, you will notice that I have uh, created three strain relationship in terms of these three lines here, wherein the dotted line here is actually the same strain relationship we are defining in our previous discussion. No? So this is simply the KD that we are discussing here. So yung CP dito is simply the KD that we discussed in the elastic stage. But since now that we are talking about control, we set aside the use of the parameter KD, since KD only happens when we are on the elastic behavior. So we might as well use the variable C, and the subscript T there simply indicates uh, a okay a control of the tension, the control of this location of the neutral axis with regards to the tensile or the tension steel provided, of course, in the tension region. And we have also the CTC and CCC here, which gives us the basis for our compression control, and CTC as the basis for our tension control. Okay, so what does that mean? So in this particular strain relationship that I plotted now, we see a region of strains wherein the beam or the flexural member is controlled by compression. And we also have a region of tensile strain which is controlled uh, by the yielding of the steel. So this is now what we consider a brittle design uh, in our old, okay, interpretation of the code, and this is what you call the ductile design in the previous codes that we have studied. Now, in between, which is this one, so this range here, in between this is what you call a transition. Okay, so it's a transition between a brittle and a tension controlled design. Okay, so what does that mean? In a compression controlled design, this should not happen in beams. This may happen in columns and other flexural members like walls, but in beams, this is not a very good scenario, no, to deal with, because it's really very dangerous. Why? Because beams fail uh, in a very brittle manner when you control your amount of steel in this region. Imagine beams are horizontal or inclined, no? So there are no other safety measure or safety mechanism that can resist or prevent rather the sudden failure of a horizontal member. While in columns, the amount of force P can actually deter a very brittle uh, failure. Ang ibig sabihin doon, sa columns, pwede ito, no? Pwede pa ito, pero sa beams, hindi. Okay? Pag beams, maganda dito ka. Pag columns, maganda dito ka sa transition. Ayan. Dito ka sa transition. Okay, these are my observations, class. No, don't quote me. You cannot see this explanation in any book. They don't explain that way because they are just providing us information. We as engineers will be the one to interpret it. But in my own opinion, this is very good for beams, attention control, and this is very good for columns. Now, in cases where you cannot avoid this region, then this is also okay with columns. Pwede pa rin. Basta meron ka lang konting safety measure na i-impose dito to add up to ductility requirement. In fact, confinement. Okay, confinement. Ano yung confinement, class? Ito yung ano yan? Lateral tie. Kapag maganda yung lateral confinement mo, kahit na dito ka, okay ka. Okay, siguro tatanong nyo, bakit hindi naiiwasan kung minsan ito? Kasi kung minsan, class, yung architect, gusto niya maliit lang yung column mo, no? Maliit yung column mo, napakadaming bakal. Tama? Okay, so hindi maiwasan yan. Okay? Kasi kailangan yan sa pag-promote nung tinatawag natin mga designs, architectural designs, state of the art, no? O kaya architectural restrictions on the design. So we cannot avoid sometimes, okay, this particular region. So that is, in general, the context of compression controlled and tension controlled sections. And the next discussion is only a matter of interpreting the ACI provisions, and I just extracted this from the ACI, which explains to us what are the specific values to use in this kind of approach, okay, in the design. So in ACI 10.3.3, sections are compression controlled when the net tensile strain, the extreme tension steel is equal to or less than the compression controlled strain limit at the time that the concrete in compression reaches this crushing strain. So this is your epsilon CU, okay? So the compression control is the net tensile strain reinforcement at the balance condition. So ito yung sinasabi ko sa inyo kanina, no? So ito yung balance condition natin dito. Ito yung limit ng compression control mo, which happens to be 0.002 for a grade 60 reinforcement, and strain are just epsilons, no? And when I solve epsilon, epsilon is simply Fy over Es. So if I divide grade 60 with 29, it will just give me, this is 29,000. The modulus of elasticity of steel is 29, so more or less 60 divided by 30 is 0.002. That. Okay? So that's it. So this is now your yield, okay? Your yield strain, which happens to be the point at which the balance condition is happening, as discussed in our elementary derivation of your raw balance. Okay? So for ACI 10.3.4, this discusses now the tension-controlled net tensile strain, which is equal to or greater than this reference. So this is now 0.005. So kung ito yung 0.002, ito yung 0.005. Okay? So this is now your excuse. Okay, so how did they get 0.005? There's no exact basis on how did they get it, but I'm sure this was somehow related to your raw max, wherein ductility was, the assurance of ductility was nailed into giving a factor of safety of 1.33 on your raw balance. So there's no exact statement on the code, but I think, and I'm almost sure that this is the basis for 005. They might not give you the same value in terms of analogy, but they are related in terms of context. Okay, so just make sure that you understand the relationship of this uh, uh, approach in the design with that of the previous code. So why? Ako ang ginagawa ko kasi, subok na yung mga lumang code no? Yung mga lumang concept. Bago ka gumamit ng bago, siguraduhin mong ano yung pinanggalingan niya, yung history. Huwag kang gamit ng gamit. Kaya nga sabi ko sa inyo, there are a lot of good software engineers in structural engineering, but sad to say, medyo kulang yung conceptual nila dito, no? Yun ang kaibahan nung nag-aral ka ng master's degree sa hindi ka nag-aral. Basta natuto ka na lang sa software. Okay? So sections with net tensile strain in the extreme tension still between the compression and controlled and the tension controlled are called transition region. Yan. So this is now your basis, okay, greater than 0.005, but not 0.04 ito, no? Because some were adjusted since the grade of steel happens to be different. No, you can use grade 60, grade 40, and even those grades that are not existent on some codes, you can use them, no? Like dito sa Pinas, may mga grade tayo, grade of reinforcement tayong ginagamit na pasado sa Philippine standard, but they are not all, they have not passed the ASTM standard. Okay? Okay, so for non-pre-stress flexural members and non-pre-stress members with axial load less than 0.10 FC prime AG, the net tensile strain at nominal strength shall not be less than 0.004. So there's a slight adjustment on non-pre-stress flexural members and non-pre-stress members, no? So this adjustment happens to focus more on beams rather than other types of members. So the use of compression reinforcement shall be permitted in conjunction with the additional tension reinforcement to increase the strength of the flexural member. So, yung pinag-usapan natin kanina are singly reinforced beams or members, no? Pero pag nilagyan mo na ng reinforcement na compression, magiging DRB na siya, no? Double reinforced. So, you have to adjust it. And how to adjust it, if you know the intent of the code, you have to know how to adjust it. Unfortunately, the code will not tell you how to do it. That's why you need to really understand the intention and go back to the basic to adjust it. Okay? So later on, we'll try to look into that. Okay, notes. The objective of introducing the concept of net tensile strain is simply to provide a unified design procedure that will be consistently applicable to the entire spectrum of flexural and axial flexural members, which include columns, beams, and other pre-stress and non-pre-stress members. So the compression-controlled strain lower limit corresponds to the balanced strain condition limit Robbie in the previous code. So in grade 40, these are the balance strain limits equivalent or corresponding the grades of steel. This is 00138 and this is 002. Again, you simply use the formula Fy over Es to get these values here. Okay, so we know that in your old design code, not old but also the new, I'm referring to the word old because this is the high what yan yung most abused parameter in ductility, which is raw balance. No? So this is actually equivalent to 600 over 600 plus Fy. Okay, times 0.85 F prime C beta 1 over Fy. Wala na yan. Over Fy siya. Ayan. So this is the shortcut of the formula. Okay. So this is beta 1. Meron beta 1 dito over M. There is a beta 1, I think. Okay. So there's a beta 1 there. Anyway, you check it out. No. So this is for SI units. Okay, for rectangular sections now, how to derive a raw TC. Okay, the raw TC here is the basis for your the corresponding raw max in the context of compression and tension controlled regions. Okay, so this is now what? An equilibrium equation. This is simply a T is equal to C. Okay, where if we define an F5 or 0.85 as M and CTC is 38 dt, how did you get this? Because in the balance condition class, we take note that this is 0.003 and this is 0.005. We just make use of a triangle, no? A similar triangle approach wherein this CTC is just a measure of the depth on the tension controlled reinforcement dt. So if you make use of a ratio and proportion, this is now valid as your CTC. Okay, so don't be confused. This is just a, a, a value of your CTC at not at the balance condition but at the ductile condition, because we are now on the tension controlled condition. This is a TC, tension control. So ASTC now becomes beta 1 over M, 38 dt times B. So if you solve for ASTC here and substitute the values here and CTC there, you just get this one. You define rho TC now as ASTC over rho BD, then this is now the formula for your... Okay, so this is the equivalent rho max. So ngayon, naiintindihan mo na. Yung rho max pala, ito lang yon dun sa context ng compression control. So, hindi na yung rho max is equal to 0.75 rho balance. Okay? And if you are going to solve for what is the multiplier here, you can just manipulate. If I ask you in the exam, what is the equivalent multiplier in this equation with that of rho TC? So I hope you can do it, because that's just a mathematical question. Okay? Now, if we recall a rho balance again, which is, tama tayo dito. Okay, tama tayo dito. Ako kasi, matagal ko nang hindi tinuturo ito, kaya minsan nakakalimutan ko din. Pero pag ni-recall ko naman, natatandaan ko pa. Kaya lang, kung minsan, sa dami ng iniisip, kung minsan nag-fail din yung memory, no? Okay. Okay, so if we recall raw balance now and divide raw balance with the raw TC or vice versa, anong kinukuha natin ngayon? Yung comparative multiplier natin, which is this one here. But class, I want you to double check this, because in our previous, in my previous lecture on this, parang may nag-question na may mali akong ginawa. And I'm very glad to admit my mistake, because sometimes yung mga errors na ganito brought about by marami kang iniisip at ginagawa. Ang importante, huwag ka mag-error dun sa concept, no? So please check this, no? So hindi ko alam kung ito na yung updated na lecture ko. Chinek na namin ito, Okay, so this are the equivalent. So kung papansin mo pala, ano ang mas ductile? Yung bagong approach ngayon, or yung raw balance approach, o yung raw TC approach? So if you will make use of this, which is less than 1, you will notice that yung raw TC mo mas maliit kesa sa raw max, kasi hindi naman 0.75 ito, no? I don't know if my interpretation is correct, but these are the things that I asked in the examinations again, and I want you to think about kasi these lectures are not lectures on the book class. These are lectures that I made when I was still starting to teach this master's degree, no? Of course, based on what I have learned when I was still studying. Okay, so this assume 2 layers of bars. D double prime is equal to 90, and DC is equal to 65. So why are we talking about layers? Okay, so I'll explain to you why. So this is the reason why. If I have 2 layers here, my epsilon TC will be measured on the extreme-most, no? Extreme-most fiber. Dito tayo nagme-measure ng epsilon. hindi dun sa gitna. Okay? Dun sa most. Hindi dito sa gitna. Okay, so that's the reason why. So we need to really take a look on this layering. And D double prime 90 is this one. Ito yung cover natin na sa centroid. Okay, these are this D double prime and DC is this one. Okay, so that is the thing here. Sorry, DT ito, DT. Okay, yung DC dun sa compression bar if there is a compression bar. Okay, so if dt over dt over d is 1.12 on the basis of this formula, so how do you apply it to these parameters here? Huh? Okay, so this is for shallow beam, and this is for not too shallow beam. It's not a deep beam, but it's a regular beam, no? It's a regular beam. So these are suggested values, I think. Okay. And if we are going to take a look on the actual values, these are the actual values. Does it fall on this or this? So you just take the average. Okay, so in actual problems, you have to check where it falls. But here, since we are deriving a formula, we just take the average of the two. And take note of what happens. Your raw TC becomes 60 and 70% of raw balance for grade 40 and grade 60 still less than the raw max of your uh, previous code. Okay, and the conclusion for that is the code which introduces this uh, approach. I think this is a 2002, started on 2002, is slightly more ductile in terms of the upper strain limit. Okay, again, I have here some comparison on the epsilon maximum. So this, please verify it. As your assignment, I will ask somebody to verify if this is correct or not. Please verify if correct, because I doubt this is the old lecture that I have. So the Bob ratio is ideal for serviceability aspect of design, and it solves the problem of bar congestion and forms well to seismic provision. So ang ganda nung ano niya, no, nung result niya pag ito yung mga ginamit mo. Wala kang bar congestion, problems, serviceability wise, wala kang problema, etc. So the net tensile strain limit of 0.004, which is actually 0.00376, corresponds to the previous code version of 0.75 raw balance. So this is now the previous version, and these are the new version of what? Ductile design. Okay? Pero sa earthquake provision class, mas mababa pa yan, ano? 0.5 ang ginagamit. Okay, so these are just for ordinary design. So in terms of the 2002 code, the following equations may be noted. Again, this is just a derivation of the 003005 scenario in your strain, and this is equivalent to CB for previous codes. Okay, so this is just a figure which relates also to these computations above. Okay, so I hope I have shared to you some very important contexts or concepts which are not new, but rather are a little bit vague and unclear to us when we design flexural members in terms of ductility. Thank you very much for listening, and I'll see you in the next video.